that we have looked at microevolution, which may or may not result in formation of a new species, we will now focus our effort towards macroevolution, the formation of species by preventing mating. Remember, a species is defined by organisms that can mate and reproduce naturally in a given environment. So, what we're going to be looking at is allopatric speciation, which results from separation of populations by geographical barriers, as we've seen before with the frog example. And then we're going to be looking at the reproductive isolation that results from allopatric speciation, the physical and behavioral barriers that really prevent mating. And these are ecological, temporal, behavioral, mechanical, gamete incompatibility, and infertility, and we will touch on all of these in a moment. Sympatric speciation does not involve geographical separation. That's a minor area with respect to how macroevolution evolves. Let's look at allopatric speciation. I'm looking in California of an example of how two species evolved from the original source. I'm looking at the black salamander in California. Now, the black salamander lived perfectly happy in Oregon. As it moved towards California, the geographical barriers were so that some of the population moved towards the coast of California and the other population moved towards the eastern side of the Central Valley. Now, the conditions on the west coast and the conditions towards the eastern part of California are quite different. Basically, the environmental challenges on one side of California and the other side of California were quite different. This barrier that resulted in the formation of two new species, because on the west side, the species evolved that could meet the environmental barriers, and on the right side, a little different species evolved that could best adjust to its environmental challenges. Now, what happened later on, thousands of years perhaps later, is that this little blue salamander comes across the little black and red salamander, and the two salamanders do not like each other. The two salamanders do not want to have anything to do with each other, therefore they do not mate. And by definition, a species is an organism that can mate. And because they will not mate, this is now completely a new species, two new species. Let's do this one, a retake on this one. Take two, because the last one really sucked. So let's go to take two, allopatric speciation. How does this work? I'm looking in California of an example of how two species evolved from the original source. In allopatric speciation, barriers develop between populations of a given species. Now, we start with a population that lives in Oregon. This population, of course, will mate and reproduce and be very successful. But over a period of time, for many reasons, these salamanders migrated south along the coast, and some migrated south along the mountain range of eastern part of California. Now, a barrier developed between the salamanders on the western coast and the salamanders on the eastern part of California. the conditions on the west and on the east were quite different. As a result, over many thousands of years, a population of salamanders evolved that could best meet environmental challenges. On the right side, a population of salamanders evolved that could meet their particular environmental challenges. Now, when the two finally meet, they do not want to mate with each other. For whatever reason, either they find themselves unattractive or many, many other barriers to mating, the two do not mate. As a result, we now have two species of salamanders. So this is an example as to how species evolved by way of allopatric speciation. Again, barriers develop that separate a population, and as a result, each side of the barrier evolves two different species. So now let's look at what happens as a result of allopatric speciation. What really results is conditions are produced that prevent mating. Basically, reproductive isolation mechanisms. These reproductive isolation mechanisms can be listed as follows. And let's look at this carefully. To start with, let's look at ecological isolation. We may find that as a result of allopatric speciation, we find that one organism lives on top of a tree and the other organism lives on the bottom of the tree. As a result, the two never get together and mate. Now, another mechanism of reproductive isolation is that over time, the mating habits change. This is referred to as temporal isolation. One organism wants to mate in the daytime, and one wants to mate at nighttime. Well, obviously, the two never get together to mate. Another mechanism of reproductive isolation is behavioral isolation. One organism has a certain mating behavior, and another organism has a different mating behavior. Now, as a result, one is not attracted to the other. Therefore, the organisms never get together. Now, if we can overcome this barrier, we still have another barrier called mechanical isolation. In mechanical isolation, the organisms evolved so that the sexual organs simply do not match up. And of course, if that happens, mating cannot occur. But let's say we overcome ecological isolation, temporal isolation, behavioral isolation, mechanical isolation, and finally the gametes manage to get together. Well, great. The gametes get together, and guess what? They will not fuse, and as a result, a new zygote does not form. And let's say if we can overcome even all of these barriers, as shown in the example, and we get the gametes to fuse, a zygote is formed, an embryo is formed, a fetus develops, a newborn results, and we get basically a hybrid, an organism that reproduces, but it is at a dead end. An example is the mule. The mule is a very, very sturdy animal, but it is a cross between a donkey and a horse. So to summarize, we can see that a number of mechanisms exist that prevent mating, from ecological isolation, temporal isolation, behavioral isolation, mechanical, gamete isolation, and finally, even the hybrid results that does not allow future organisms to evolve. So taxonomy is the classification of living things. Now, taxonomy goes back to the Linnaean system, which basically utilizes two names to describe a given organism: the genus and the species. For example, Homo sapiens describes humans. Homo refers to the genus. Sapiens refers to the species. If we look at the overall scheme, we recognize that organisms are broken down into a hierarchical system. Kingdoms are broken down into phylums, phylums into classes, classes into order, order into family, family into genus, and finally genus into species. And we describe an organism by using the genus and the species in combination. Now, based on similarities in structure, often referred to as morphology, we can construct evolutionary trees, or perhaps we might refer to them as cladograms. Looking at the Linnaean system of classification, we can see from this example the animal kingdom broken down into phylums, the chordata being one phylum. The chordates can be broken down in a number of classes. One of the classes would be Mammalia. If we break down the Mammalia into orders, we see the carnivores. We break down the carnivores into families. One family is the Felidae, and we can break this down further into the cat, the genus Felis, and finally into the domestic cat. So this clearly illustrates how the overall classification system works. Now, the classification system is based on looking at similarity in structure. Homologous structure connote a common origin. Look at the bat wing, look at the wings of a bird, look at the arm of a gorilla. All of them have similar structure, which means that they're homologous and they probably are related. Therefore, all of these organisms have a common origin. Now, analogous structures does not indicate common origin. Believe it or not, that the little pern, the leptoptern, I believe that's how it's pronounced, the leptoptern and the horse may look alike, but if one carefully examines the foot, that these two really are not related whatsoever. So let's construct a family tree of carnivores. We can see that the carnivores evolved about 60 million years ago, and we had a common ancestor that sprung up to become a dog. And you can see the evolution of the weasel, the walrus, the seal, and so on and so on. And so we can see how one organism is the ancestor to another organism, and the evolutionary tree is often depicted in this fashion. Okay, the cladogram is another way of illustrating relationships by looking at shared derived characteristics. If we look at organisms like the lizard, the deer, the lion, and the seal, we can see that at one point all have 4 legs. As we move past the lizard, we see another break that tells us that above the lizard, all the organisms have mammary glands. And then if we move further up, we see that above the deer, all those organisms are carnivores. And then if we move above the lion, we see that all the organisms above the lions are aquatic. And so we can see how these organisms are related by certain shared derived characteristics, and this is again referred to as a cladogram. Okay, the cladogram is another way of illustrating relationships by looking at shared derived characteristics. If we look at organisms like the lizard, the deer, the lion, and the seal, we can see that at one point all have 4 legs. As we move past the lizard, we see another break that tells us that above the lizard, all the organisms have mammary glands. And then if we move further up, we see that above the deer, all those organisms are carnivores. And then if we move above the lion, we see that all the organisms above the lions are aquatic. And so we can see how these organisms are related by certain shared derived characteristics, and this is again referred to as a cladogram. Often when we compare a cladogram with the classical evolutionary tree, we can see significant differences, and there are pluses and minuses in illustrating relationships by way of the cladistic approach as well as the classical phylogenetic tree that you see to your left. That's the end of the show.